you're one of the few guests I've had on that like was working in the industry during the .com bubble and
Yeah.
subsequent bust. And obviously you work with undergraduate students now who are graduating in 2022 and 2023. And the last 2 years, at least compared to the 5 years before, have been really rough in the industry.
Mm-hmm.
I'm curious to get your take on like, is it similar? Was it way worse in 2001 from the perspective of like working in the industry, trying to get, your first kind of development job? Before we jump into today's conversation, I've got a recommendation. Jonathan Hall, a friend of mine who was on the show 10 or so episodes back, well, he's got his own podcast that you should definitely check out. It's called Cup O Go, and we do talk a lot about Go development here on this podcast, but we also talk about a lot of other stuff. And Cup O Go is a great podcast if you really just want to keep going deeper on the Go programming language. So Cup of Go check them out. They're on all the major podcasting platforms and on YouTube. Welcome to Backend Banter. I'm super excited. Today is extremely special. I've got my college professor from about 8 years ago on the pod to talk about distributed systems, and we might even get into a little bit of Go. So Dr. Russ Ross has a PhD in computer science and specifically distributed systems, and it was in his distributed systems class that I first learned about Go, again, about 8 years ago. Do you want to take just a second and introduce yourself?
Yeah, I'm from Southern Utah. I grew up here, so I'm actually a native of St. George. And then I left for college. I went to Harvard University and did my bachelor's degree there. And then I stayed in the Boston area and worked for a startup during the .com boom and was there when the bust happened in about 2001, 2002, and the whole industry sort of collapsed. The startup I was at went from about 150 people down to about 25.
Wow.
And I was pretty much one of the two engineers still there. And I was by far the longest tenured engineer at the company. And it's like all my friends had left. And so I kind of wanted to leave too. And I was trying to figure out what to do next and decided I wanted to, I had a number of friends who went to graduate school, and that sounded like kind of a nice, different thing to do. And I really wanted to go to England. So I just applied there and ended up getting into Cambridge and went and did my graduate work there. And then I've been here at Utah Tech. It was Dixie State for a long time. But ever since then, I came straight out of grad school. So.
I didn't know about that middle part of the story. So you went and got your degree at Harvard and then went to a startup. There was obviously the .com bust. And so that was what pushed you into kind of going and pursuing a PhD at Cambridge, or do you think you would have anyways?
I had never really thought that much about graduate school. I mean, I think that was part of growing up in Southern Utah. I never knew anybody who went to graduate school. It was just something that had never occurred to me. And the startup I was with was, it was a Harvard startup. It was some people in the class ahead of me, and I was recruited by a friend in the program. And so that was a fairly unusual group, I guess, a lot more academically minded than most startups probably. And as the economy started to deteriorate, most of my friends were all rather than going for another company, they headed to, several of computer scientists went to law school and became lawyers. One of them is now actually a Hugo-winning sci-fi writer, and then a couple more went to graduate school in CS. And I remember actually about the first time I ever thought about it was this particular friend who was headed to graduate school. I think he went to Berkeley. And just kind of on the way out the door, he was like, yeah, and I should see you at graduate school too someday. And it kind of never occurred to me that, oh yeah, that's a thing I could do. I had a lot of moments like that actually, where, and I think that's true for a lot of people. It's hard to picture ourselves doing things different than what our parents or our friends did. And for me, it was actually kind of a big moment when I recognized that, oh, these things that I never thought I could do, that all I have to do is apply, right? That's actually a possibility for me. And so that was actually a pretty big deal. And then I applied to Oxford and Cambridge and got into both. But Cambridge has a much stronger systems program. Oxford is really stronger in kind of theory, or at least was at the time. And so I ended up going there. And yeah, but it was encouraged just by the fact that so many of my friends were doing that. And
Yeah.
so it's like, oh, maybe this is a good possibility. And I was kind of burned out working at a startup. I found that when I'd go home at night, I didn't want to work on anything on a computer. I just wanted to stay away from a computer. And that was really kind of distressing for me because I'd been in love with computers for so long. And the thought that my job was kind of ruining that for me. So I really just wanted to change the scenery for a little while.
Yeah, that makes a lot of sense. I'm curious, having gone through, you're one of the few guests I've had on that like was working in the industry during the .com bubble, and
Yeah.
subsequent bust. And I'm curious if, I mean, obviously you work with undergraduate students now who are graduating in 2022 and 2023, and
Yeah.
the last 2 years, at least compared to the 5 years before, have been really rough in the industry.
Mm-hmm.
I'm
Yeah.
curious to get your take on like, is it similar? Was it way worse in 2001? From the perspective of like
Mm-hmm.
working in the industry, trying to get your first kind of development job.
Yeah. I mean, my perception, I guess my perspective's a little different, but I feel like the one back then was a lot worse because it really was kind of the whole industry, and it was, it brought the whole economy down with it.
Yeah.
I mark the beginning of the bust. I think it was March 2001 was when the NASDAQ peaked. Of course, nobody figured that out for 6 months
Right.
after that's when it began. But
You think it's going to come back or something, right? Like you don't.
yeah, but back then that was the first big boom we'd had in the internet was brand new still for most people. It had been public for less than a decade. All this idea of e-commerce and internet companies was a brand new idea, really. And so when it collapsed, it really felt catastrophic. It's unclear, was this just an illusion that it's gone forever? Nobody really knew.
Right.
And although I have to say, even then, it never occurred to me that it would be hard to get a job. Like even then, I was being recruited by colleagues that had gone to other companies. I kind of feel like all of these things, the public perception of it is always worse than the reality. And I think that's even more true this time. There have been a lot of obviously high profile layoffs from the big giant tech companies, but I think they've still just laid off their way to about their 2001 staffing levels.
Yeah.
It came from just a tremendous overhiring. They kind of got into this weird frenzy where all the big tech companies wanted to hire everybody just so their competitors couldn't. That's basically what was
Right.
happening. And so this correction has hit the really high profile companies, but it hasn't hit the rest of the industry as much. And it really feels a lot more like just a correction from a short-term excess. So like, I don't really think it's what do I know, right? But it doesn't look to me or feel to me like a big structural problem that's going to have lasting consequences. It feels like a much shorter time. Now that still sucks for students who are graduating now because the hiring market's going to be terrible for a couple of years. But I don't think it's, and here's where I think having a little longer perspective helps. I still think this is an amazing industry to go into with basically unlimited opportunity when you look over the medium to long term.
That's what I've heard from some other guests as well, and I tend to believe the same. Nothing existentially seems to have changed. Like interest rates have gone up, right? Hiring, as you mentioned, seemed to be just excessive. And just anecdotally, I've noticed the same thing. Smaller companies. I mean, my company, we just hired like last month. It's like if you didn't have too many people, there seems to just not be that many layoffs happening.
Yeah. So. Yeah. Because again, I don't think anything has really triggered it for most of the industry other than, this excessive hiring. And then, there's a certain amount of just kind of cloud cover companies that are like, ooh, we've kind of been wanting to get rid of this and, this division, or we overhired. And it's kind of gives everybody an excuse to do that without too much scrutiny. They can say, well, it's the whole industry. So I think there's been a certain amount of that too. But
I also think, like you mentioned, you didn't have too much trouble. And I'm sure to a lot of people listening to this, it's like, okay, well, you went to Harvard, you went to Cambridge. There is a certain truth, I believe, to just like, if you're one of the best, you won't struggle as much, right? Like when times are really good, it's easier to get into the industry. when when times are good, you can get in with like the bar is lower, I guess is the way I'd phrase it.
Yeah, sure. Yeah, it provides a lot of extra opportunity. Um, but yeah, I think if you're good at what you do, okay, I mean, look at it at the kind of the macro level. There is just so much more demand for people who can write software than there are people who can do it. And that gap is growing, right? The need for software is increasing dramatically across all industries. And the number of computer science graduates coming out is not keeping up even close. I think the deficit between demand and supply is continuing to grow, and I think will for a long time. And so, structurally, there's again just a lot of opportunity out there, and you have these shorter term fluctuations. But I think if you're good at what you do and you've like developed skills in really valuable areas, I think you're always going to be in a pretty good spot. Maybe your local area is having a rough time, and again, you're going to have these short term um, ebbs and flows of the market and things like that. But I still feel very optimistic about the industry in even the medium, even just go out a year. I think everything's going to look pretty different. Probably, maybe there'll be an economy-wide
right.
recession, and that'll change things. But I think as far as the industry itself, I don't think we're anywhere close to being overhired for kind of from a longer term perspective.
That's my perception as well. I want to we might circle back to this topic, but I do want to start to move into and talk a little bit more about distributed systems specifically. Yeah. So you did your doctorate on distributed systems. I know I'm being extremely vague here, but let's start with something really basic. I'm a big believer in, if you're getting into this industry, it can be extremely useful to go deep on like weird esoteric topics, even if you won't necessarily use them day to day. I think it just makes you a much better engineer. Could you explain to us in like just simple terms, like what is a distributed system and how does it differ from a non-distributed system?
Sure. Yeah. I mean, it's pretty straightforward, really. Anytime you have more than one computer cooperating on a task, I think you've got a distributed system. So something as simple as a web browser connecting to a server, right? There's distribution happening there. That's about the simplest form, a straightforward client-server relationship. But that's the starting point, and pretty much everything more complex than will fit on a single computer, or something that has to be replicated, or have the ability to fail over if a machine falls over. All right, all of those things are distributed systems. And there are some fundamentally different problems that arise in distributed systems than we see in single node systems. And so the way that you design for them and the kinds of problems you have to solve, I think if you don't go into it recognizing you're doing a distributed system with those problems in mind from the beginning, you're going to paint yourself into a corner, and have to make major structural changes to the work that you've done once you discover that that's where you are.
Right. So when I look at like the last 10 years or so of web development, there's been a lot of kind of hype and excitement around certain things like moving to Kubernetes or using single page apps on the front end. I just talked to the guy who wrote the HTMX library. I'm not sure if you're familiar with that one, but basically there's been like this ebb and flow of like, how much complexity do I need in my architecture in order to like handle scale and reliability? And then there's like this pushback of like, oh, you added too much complexity.
Yeah.
What are some of the heuristics when we're working with distributed systems? Like, I guess the question is like, why would I introduce distribution into my system at all?
Yeah. And I think you should avoid it unless you need it because of that complexity. Things are less efficient generally when they're distributed. There's a lot more complexity just from the fact of distribution. And so I think if your problem is something that can be solved on a single node, you should push that as far as you can. I think all too often we're kind of seduced by just the challenge and the interest of making something that's a little fancier. And so, I love things that are complex and messy. That's what I enjoy. And so I'm always kind of looking and saying, yeah, how could we, how could we make this a bigger problem? But I think that's actually been kind of a mistake that a lot of systems made, or that's tempting to make, is to say, well, and I think the thinking often goes, this is how Google does things. This is how Amazon does things. I want to be big and, take over the world like them. And so that's how I need to do things. And, that's probably a mistaken way to think about it. So Jeff Dean at Google once, in one talk, he talked about ways to think about system evolution. And one of the things he said was, you should always be designing for the future to some degree, but not too far out. And so I think he said you should probably be aiming, thinking about what if your system gets 50 times bigger than it is now. I forget the exact numbers, but he said, don't try to plan for anything like 100 times bigger. If you
Right.
do, you're probably going to be solving the wrong problems. And like he cited, some examples of Google in its early phases. They were building things using hard drives, and trying to learn how to scale with it. And then at some point they realized they had enough machines that they could just move the entire Google index into RAM. And that fundamentally changed how they designed it. He said, if we'd been planning for 1,000 times bigger than we were, we would have just had to throw that work away anyway, because we didn't actually discover where the real problem was until we got there. And I think that's true, again, on every scale. You should always be looking at where you are, planning for a reasonable amount of time in the future, but recognizing, I think it takes a little humility actually to recognize you're not going to guess right. You're not going to anticipate what the real problems are until you get there. Your customers will change, the hardware landscape will change, whatever it is. If you're trying to anticipate that and plan for, create this giant complex artifact, you're probably going to be solving the wrong problem.
I've heard the heuristic, like an order of magnitude, kind of plan or be ready for like an order of magnitude. Like you said, 2 orders of magnitude or 100x.
It's probably too far. You're probably, because I think you always think that bottom end of the scale, but there's kind of a top end too. And if you're trying to think that far, you're probably wasting effort.
Yeah. And realistically, in my experience, like an order of magnitude for growth in your company happening over the course of a year is amazing. Like you're in a really great spot.
Yeah. And you're either so small that order of magnitude isn't actually that much anyway, or, you've got the kind of problem where that's great to have. And
right.
We all wish we had that problem.
So you mentioned something interesting that I think is a really good rule of thumb, especially for people that are kind of new to web systems, particular backend systems. And that was, you said, kind of try to keep it on one box until you can't keep it on one box anymore. What do you mean when you say that? Could you give like maybe an example of a system that would outgrow a box?
So if you're looking at a standard kind of web architectures, we talk about 3-tiered architecture. You have the client, the web browser, you have the server, and then usually the database is a separate machine. And that's usually a good place to start. And then you look and contrast at some systems like Amazon Web Services databases. They have these, DynamoDB, and Google has Spanner, and they're these big, complex distributed systems. And again, it's kind of tempting to go from that really simple architecture and to say, well, we're outgrowing this, let's go to this really bigger one. But I think an interesting example is to look at Stack Overflow, which is an enormously popular resource, and they still run off just a handful of machines.
Oh, really?
It's surprisingly, every once in a while they publish details about it. And if you go and look at the specifics, it's kind of shocking how little they have invested in the hardware. Because they just said, let's just beef things up on a few machines, and you get much greater efficiency with a simple architecture. You just don't get unlimited scalability. But again, unlimited is not a real thing. And so,
right.
But I'm reminded of, there was I wish I could remember, there was somebody posted, I think it was a blog post from 10 years ago, when big data was the buzzword everybody was interested in. And he went to an interview for a startup, And in the interview, they said, we work with Hadoop, which is the open source version of MapReduce, a framework for distributing computation, like data analytics computations across a bunch of machines in a
Yeah.
cluster. A cool system, really, really interesting in things. And they said, okay. And they gave him a USB drive and said, here's a data set he opened it up and it was like 200 megabytes or something. They said, how would you architect this to work on Hadoop? And he was, a little confused and said, "Oh, is this just like a representative sample of your data or something like that?" And they're like, "No, this is our data set." And and again, I think they've kind of gotten caught up in this idea. It's like, oh, we're working with big data. What do you do with big data? You spin up a Hadoop cluster and decide how to partition your data out and things like that. And he's like, well, what I would do is write a Python script and like load the whole thing into memory and just run over a for loop,
Yeah.
which is absolutely the right answer for a 200 megabyte data set. And so, I think recognizing like a lot of those distributed data processing systems have become almost less necessary, as you can now just go buy a server with a couple terabytes of RAM.
Right.
And, and 100 CPUs or whatever.
Which is a lot of RAM.
Which is a lot of RAM and a lot of CPUs and a lot of computing power. But if that is sufficient to solve the problem you need, I mean, those are expensive servers, those are a few tens of thousands of dollars, but that's a lot cheaper than a group of engineers over, the course of several months designing out a distributed architecture. So,
Right.
When we say, scale vertically, right, the old term, just get your machine more and more powerful. I think we underestimate how far you can go with that. We kind of go and look what's the biggest Amazon web service, EC2 instance that I can rent. And that's probably not the right question. You should actually be thinking, what if I just bought a server big enough to solve my problem? And that doesn't work for everybody, right? That's not always the solution, but it's probably the solution a lot more often than we kind of want to admit. Because, right, we want to be the grown-up solving big, hard problems and justifying our interest in complexity.
As a DevOps engineer, you might recommend your way out of a job.
Yeah, right. And so, again, I think distribution solves some real problems. So one of them is reliability, right? There's just no way to make a single node completely reliable. So if you need, 5 nines or 4 nines or 24/7 uptime, whatever it is, some kind of distribution is a requirement. That is the only way to make something reliable, right? You have to make it so that when some piece of hardware inevitably fails, it doesn't take down the system. So that's one place where you don't really have a choice. And so it is solving a very real need. There are lots of ways to go about that. Maybe it's just replication and failover. Maybe it's something more complex than that. But that's one that absolutely demands distribution. Outgrowing a machine, right? Your storage needs are too big. Your computation needs are too big. That, again, really calls for a distributed system. Having things, maybe latency is an issue. You need machines that are close to your customers because the speed of light isn't getting any better. And so there are some reasons that you absolutely have to do it. And, again, I think distributed systems are really interesting and really fun, and they solve some very real problems. But I also kind of feel like we've probably over-engineered a lot when, we probably we should have started with simpler systems and then evolved our way to the need, in many circumstances.
So you mentioned a couple interesting benefits of distribution there. So I heard kind of availability, reliability, scalability, and kind of latency, at least 3 of them. There may have been more that I missed. I recently had Glauber Costa, he's the CEO of a company called Turso on, and they do distributed databases, right? It's kind of edge databases. And in my experience, stuff like that, or we could even maybe take a step back from data, but just say edge compute for your website, seems to be pretty trivial in the sense that some other company is doing it for me. So it's easy for me to just deploy to GitHub pages or whatever. And they're taking care of I'm sure it's not trivial under the hood, but fairly trivial to implement in my web app. I have a question about scale though. Like you said, sometimes we don't need to scale horizontally rather than vertically. We don't need to add more machines because one machine
Mhm.
will actually do for the size of the data. Do you think that that's changed over the years? Like if we back up 10 or 15 years, like would the kind of threshold at which you need to go wide rather than go tall, was it
Mhm.
much lower, and it's just a result of like Moore's law uh, going forward that we can now just kind of be lazy and slap it all onto a single box?
I think there are a couple of trends that have made it more feasible to do more on one machine. And one of them absolutely is just the scale of modern machines. The RAM you can get, the number of CPUs can get, even though single threaded performance is not speeding up nearly as much as it used to. So that's one of them. And I think it's easy to underestimate, unless you're actually going and looking what's out there, it's easy to underestimate how big machines can get these days.
Yeah.
If you actually buy them and deploy a customized machine. Um, there's also, I think, a greater trend toward one that I'm just starting to see a bit more that's probably related to Moore's Law winding down, which is there's kind of a move back toward statically compiled languages and a lot more caring about
Yeah.
raw performance, right? For a long time, the kind of mantra was performance doesn't matter, right? Write it in whatever makes the programmer the most productive. And then in a couple of years, the machine will have sped up enough that whatever performance you lost by using Ruby or PHP or whatever will kind of been made up for by just buying a faster machine. And
Right.
so the argument then was if you're wasting your time, programming in a more efficient language that takes longer to develop on, you're probably actually that's a waste of time and effort. Like that's actually a bad decision.
Bad return on investment, right? Yeah.
Yeah, yeah, and that's kind of changing now, and I think that's partly also being driven just by the LLVM project that has made it practical now to make a good quality compiler for a new language. That was incredibly hard to do for a long time, and there were all these languages being written for the Java virtual machine, not because that was a good platform for them, but because it did a lot of the work for you. And so that
Right.
was the easiest way to bring a new language and get reasonable performance. But so now
What
we
is
have,
that? Could you
you know,
explain just like high level
oh,
overview, like
sure.
what changed the game with LLVM?
Yeah. So compilers are enormously complex. If you want them to actually be efficient and generate really good code, that just seems to take, a few decades of effort. And so if you have a great idea for a language, some new idea that you want to incorporate in there, you're a language designer, you have this problem you want to solve. Are you really signing up for like 2 decades before it's usable? Um,
Yeah.
we saw very few languages with their own compilers for a long time. Haskell quite famously compiled to C and then fed it through GCC. All the
Right.
JVM languages ran things through the JVM. Go was kind of an exception because they had a compiler kind of sitting in their back pocket from previous projects. They had a C
Hmm.
compiler that they'd already built, and they were able to kind of adapt that. GCC was the big open source compiler, but GCC is kind of hostile to adding new languages to it. It's structured so much like C internally and things. And my understanding, there were actually deliberate decisions to not re-architect it like back in the 90s to make it more friendly to different kinds of languages.
Oh.
There was some kind of Richard Stallman thing, so I understand it. And
Fair
so
enough.
so LLVM was Chris Latner, who was started this project, and that's where Clang comes from. That's the C front end for it, but it stands for low level virtual machine, and it's basically all the parts of the compiler as a library. And so if you want to make a new language, so like Rust uses it. So Rust, making the compiler is still a lot of work, but once you get it kind of far enough in the process, you can then just bring in a lot of pre-built optimization passes and code generators from LLVM that kind of come out of the box. And now it's pretty easy to target a bunch of, to target it for Intel and ARM and RISC-V and, kind of target different architectures. You don't have to start from scratch on each of those. You can kind of inherit those from the project. And so now it seems like we're starting to see, instead of all this interest in languages that are kind of easier to implement, right? Scripting languages, part of the, making one is it's easier to write an interpreter than a compiler. And,
Right.
but it really feels like now we're getting a lot more kind of compiled languages that are a lot more mature, a lot quicker. And I think a lot of that leans on the LLVM. But I think there's also this greater necessity for it as we're starting to say, well, the speed of computers seems to not be getting that much faster rapidly. And so we kind of need to now start rethinking and saying, well, if this is the performance envelope that I have, what can I do in that window? And a lot more people are caring about absolute performance than they used to. And it turns out I think rule of thumb for like Python and Ruby was always it's 50 times slower than C or C++ for algorithmic
Right.
code, right? In practice, it's mostly talking to the database and things, but that's a lot of speed, right?
Yes.
That's a lot of performance on the table. If there's no longer this promise of Moore's law will just save us all in the future, and it just kind of comes for free to software people, then it starts to change the way you think about it, and you start looking at Go and Rust and other languages like that bring in more modern features and are more ergonomic to program with than older compiled languages, but also offer a promise of really good performance.
I
So
mean,
so I think that also increases what you can do on one node if you're just going at saying that efficiency is actually an important part of the problem, which for a long
right.
time it kind of wasn't. Yeah.
I was working on a project. This is 4 or 5 years ago. Ruby project, CPU
Mm-hmm.
bound Ruby project, and yeah, rewriting it in Go, we literally saved tens of thousands of dollars in our AWS bill because we went from like
Wow.
40 servers on a Kubernetes cluster down to like 3 or 4. Um,
Wow. Yeah.
it's
That's
it's it's
incredible.
yeah, it's like it doesn't matter until it matters, and then it
Yeah.
matters.
Yeah.
uh,
Yeah. And what we'd really like to have is a language that's just as productive from the beginning and performant, right? We
right.
want to minimize that trade off. And,
Yeah,
and
and
I think we're getting better at that. Yeah.
I think we are too. There's been, especially in like the last 1 or 2 years, I've definitely seen a trend online of people enjoying static typing, not even because the statically typed languages happen to be faster, but they
Mm-hmm.
also can have productivity benefits, especially if you have like modern things like type inference, right? So you can still get
Yeah.
a lot of the benefits without quite as
Mhm.
much verbosity and things like that.
Yeah. I mean, static type systems eliminate entire classes of errors, right? There's great things to be said about them. They are, and that's good for productivity and correctness of your code and things like that. But I think for a long time that came with a lot of overhead, right? It felt like if you're programming in C++ or Java for a long time, it felt like you kind of there's a lot of extra work just working around the idiosyncrasies of the type system. It was kind of, okay, there's this benefit, but there's this big price I have to pay to get that benefit. And I think, um, yeah, we're getting better with our type systems and things like that to where they stay out of the way a lot more. It feels more lightweight while you're writing code. This is something I always felt in Go, especially. Go
Yeah.
values simplicity as kind of one of their defining virtues, and does feel like I always thought of Go as kind of this weird merger between C and Python. It's
Yeah. Yeah.
kind of drew ideas from both of them. It wasn't either of those languages, but it made sense to me to think of it in those terms. And I always felt in Go, I didn't feel like I was spending a lot of time just kind of fighting with the memory model or the compiler. That didn't it felt a little more onerous maybe than Python would, but it didn't feel like that much more. And I felt like the gains I got from it were well worth it. And I've always kind of I like compiled static languages. I like strong type systems. I've been dabbling in Rust recently, and that one it feels like there's a big cognitive barrier and things, a much steeper learning curve. But it's there's also a lot of things about it that are really nice and convenient as a programmer. Things that I think they drew a lot from OCaml.
Yeah.
It was written in OCaml originally, and they drew a lot of OCaml ideas, even some syntax there which I think is a great source. I used to program in OCaml and for a few years, and I did a lot of stuff in graduate school in OCaml, and yeah, there've been better ideas out there, but again, there's always been this problem. How do you get it into a new language people can use? Now again, there's this 2-decade compiler writing barrier.
Right.
Or that's to get it to where it's really industrial strength and competitive with GCC or whatever. And so
Yeah.
so I think it was just hard to bring those good ideas to the mainstream. It was such an overwhelming undertaking to bring a language forward like that, that very you pretty much had to have a big corporate entity behind it, and that just wasn't what they wanted to do.
Right. That's so interesting. So LLVM, kind of like an abstraction over a compiler almost, if I'm understanding correctly.
Yeah.
Plug and play compiler. Do you think that, so Go is famous for kind of having this very fast compiler, right?
Yeah.
And I think a lot of that is due to how small the language is. Like it's probably
Yeah.
easier to write a fast compiler. Do you think that any of that has to do with them not using LLVM? And it's okay if like you don't know. I know this is kind of an on the spot question, but
I guess I don't know enough about LLVM, but there are also aspects of the language that can be designed to make it faster, or conversely, there are ideas you can avoid that would have made it slower.
yeah.
Like C++ is famously very slow to compile, and some of that is structural. So Mike Burrows at Google had a story. He was compiling something on their distributed compilation farm. It was a C++ project, and I think it took like 45 minutes to compile. So
on a distributed like compute load.
Yeah.
Wow. Okay.
Yeah. So he was, had plenty of time to sit around and think about it, I guess. And that old XKCD.
Yeah. Sword fighting.
Yeah, exactly. And so he looked and was kind of monitoring it and saw some header file go by. He's like, I didn't include that. I know my code. We don't think we used that. And so he investigated it a little further and found that the project was indirectly, through includes that it brought in other includes, was parsing it and compiling it. I think it was 50,000 times. This header file, he didn't know he was using at all. And it was starting, it was being read in and reparsed 50,000 times over the course of the compilation. And just the way C++ works with these nested includes, it's kind of.
Was it circular? Was it a circular include, or would?
I don't know the details of it. But that was, yeah. But what he said, and so, and I think they're that, and there are other aspects of C++ that just kind of make compilation expensive. When you compile something, it just has to look at too many other parts of the project. And so if you design it so that each compilation unit, each file really can be compiled independently with minimal consultation of other files, if you kind of design that in and watch for the points where it ends up, you get this kind of explosion in complexity and avoid those, then that actually gives you, I know the Go team talked about that in the early days. It was partly the design of the language. They made decisions that could keep the compiler faster. And so it's a combination. It's not just the infrastructure they were using. But I don't know how much, I don't know where, LLVM stands in that. How fast you could go if you put Go on LLVM. I don't know how that would compare to the
right.
I think it's an interesting question, but
no, that is really interesting. I feel like I've definitely learned something so far on the podcast. So I want to circle back a little bit to distributed systems and talk about, okay, let's assume that we've got our box, and even in 2023, we're running our server and we're kind of hitting the upper limits of at least what's reasonable for our single server. And so it's time to distribute it. Maybe we're moving to Kubernetes and we're running Docker images in parallel or something like that. What are some of the biggest foot guns? Like, we talk about this explosion of complexity when we start distributing things, but like, what should we actually worry about, at least on the front line?
Well, let me just step back for a minute and talk about, like, I said earlier, there are a few fundamental differences between distributed systems and single node systems. And I think part of it is being aware of those and then, avoiding situations that make them worse. So like the most obvious one is latency, right? There's going to be network time, and again, the speed of light limits this. So if you got systems on the East Coast talking to systems on the West Coast, there's going to be some time for those messages to go back and forth, and that's going to slow things down or make it different than a local system. But that's kind of fairly obvious, and it's kind of the easiest one to deal with because it's in your face right from the beginning. And we're actually pretty good at reasoning about that. And we can just kind of hide it. If you're typing in, Google Docs and it takes time for it to save your changes to the server, it just does it in the background and you don't even notice,
If your
right? We're
UI
pretty
is
good at,
good, then it's good at hiding
yeah. Or
it.
there are other places where we can just have things overlap and, that's something we can kind of deal with. We're pretty good at that.
Yeah.
A second fundamental difference is you don't share an address space. So you can't share data structures by pointers. You can't cooperate on shared data structures in the same way. And so, you got to have a good RPC library that marshals data up and sends it across and be aware that those changes are not being shared. Again, it's another one we can kind of library our way out of it. And again, I think it's one that's obvious enough and in your face enough from the beginning that you're not going to get that wrong. That's
Yeah.
another fundamental difference. These are, by the way, from a paper by Jim Waldo and his collaborators called "The Note on Distributed System" from back in the '90s. That was kind of a foundational work for a lot of practical distributed system stuff. A lot of
As you
people didn't
say
understand
this,
these things.
as you say
And
this,
so,
I've seen both
yeah,
of those things go very wrong. So I'm very excited
yeah,
to hear what the actual Bigfoot guns
yeah,
are.
yeah. And so, but the third one that it really is kind of the defining problem of distributed systems is partial failure. On a
Okay.
single node, your system's running or it crashes, pretty much, right?
Right.
And so when you get into a distributed system, you can have some of the system fail and the rest of it keeps going. And the whole point of having a distributed system is you want the system to keep going even when parts of it fail. So
Right.
it's not good enough to say if anything fails, we shut down and reboot. That's just a non-starter. And partial failure could mean a network link goes down. Machine A can send packets to machine B, but B can't send them back.
Hmm.
You can have weird topographies where messages get through sometimes and in some directions, but not others. You
Yeah.
could have 50 machines and 20 of them can talk to each other and the other 30 can talk to each other, but those two groups can't communicate. You can have a node that fails and then restarts, I guess, or is down permanently. You can have a node that just slows down. Google once had a bug where some of their machines were booting up and disabling the cache. And so they were running, but they were just, 100 times slower than the other nodes.
Yeah. No big deal. Okay.
And so they were participating in the system and timing out in weird ways and things like that. And so in a distributed system, you kind of have to just constantly be asking, okay, what if this fails, right? Anytime you talk across the network, you send a message out, you don't get a reply. Is that because the message didn't make it to the destination? Or did it get there, they process it, and the reply didn't come back? Do I
Yeah.
retransmit? Are they dead? Are they coming back? Are they there processing now and I just can't get acknowledgments from them? You never know for sure. And this is something you can't just take a system where you ignored these issues and go and fix it up later. You really have to think of it from the beginning. Any decent RPC library requires every RPC call has an error return value. There's always the possibility of an error, even if your API doesn't allow for one,
Right.
because you always need to be thinking about how things could go wrong. And that's again, kind of the defining challenge of distributed systems is we're just constantly thinking about all the different ways that things could fail, and they can just fail in so many more ways than a single node can.
So,
So, yeah, go ahead.
yeah. Sorry. So I was going to say, so you've got a bunch of nodes in a system, and this fundamental problem, if I'm understanding it correctly, is one node's reaching out to another node, say sending, like, very simply, we could just say it's sending an HTTP request.
Mm-hmm.
And for whatever reason, it doesn't get a response. But can that just not, it just can't be known exactly why if you don't get a response, whether that request's been processed, response didn't come back, it was never received at all. Is that just something that can't be known? And so we design distributed systems around that? Or is that something that we can figure out?
In a general network model, that's impossible. So one of the foundational proofs is called the FLP result. I'm trying to remember what the paper's actually called it. So the initials of the three authors, and they proved that consensus in a distributed system is impossible if even one node is allowed to fail. or you need one part of the system
Hmm.
basically. And so it's a pretty, excuse me, a pretty um, devastating result and impossible. It's like, you try
Yeah.
and find an algorithm that works around it, and they prove no algorithm can do that.
Yeah.
And so you have to make some stronger assumptions about the network, because in practice, distributed consensus is one of the main tools we use. Paxos and Raft
Hmm.
is just one of the basic tools we reach for now in almost every distributed system. But they have to make assumptions about timeouts and things like that, and they always have a footnote that says, yeah, in the worst case, we may just never actually be able to come to agreement.
Right.
It's unlikely. We've mitigated it pretty highly, but they all recognize there's this result that shows that, yeah, in the worst case, this machine fails, then it comes back up, but this one fails, and if it really goes south in the worst way, you're never going to be able to come to even a basic agreement on one a bit should be 1 or 0.
Right. So we
And
have these fancy algorithms to like make sure that it's as good as we
yeah,
can get it, but fundamentally there's some tiny probability that the system
yeah,
goes down.
yeah. And so in practice, if our machines are working well enough, we get pretty good, reliable, fast consensus, and we can solve lots of practical problems.
Yeah.
But yeah, it's a hostile landscape, and it really is fundamentally a challenging problem with some pretty hard limits to what we can guarantee will happen in every case. Um, and just think about the problem. There's also like the cap theorem, which says that if you want consistency, availability, and partition tolerance, you really can only have 2 of those 3.
Hmm.
So you can make sure. So this, like, think of a database, like a shopping cart. If you save to a shopping cart and then you want to be able to read and see what you saved in there and guarantee that what you saved in it is what you read, for a separate transaction, that's consistency. You want to make sure that the last changes that were made to it are available for read. Availability says, yeah, it's really important that I actually be able to read what's in there, right? That it doesn't just say, oh, I'm unavailable right now, come back.
Right.
And then partition tolerance deals with what happens when the network segregates into a couple pieces and the parts of your distributed system can't necessarily talk to each other. And so the reality is partition tolerance is something, partitions happen in networks. We work really hard to make them not happen very often, but they do. And so you're really forced in any large system to choose whether you're going to be consistent when that happens or you're going to be available when that happens.
Is there a
And that's
popular
something,
answer?
again, it kind of goes back and forth. It depends on your priority. Google tends to do things in the consistent side, and then try to mitigate availability. So
Hmm.
like the Spanner paper was really kind of a famous one in that regard. Whereas Amazon for a long time was kind of champions of availability over all else. With the shopping cart specifically, they said, if a customer clicks buy, we want the transaction to go through.
Right.
Right? That's
Yeah.
the most important thing for us. And it's you, most of the time you get both. Most of the time you get everything, but they would prioritize that. And so maybe you deleted something from your shopping cart on one machine and then turned to another machine and hit buy, and they got out of sync a little bit, and they say that's okay if that happens once in a while, and we'll probably figure it out later. And maybe it's a
Yeah.
customer service call that fixes that.
As long as
But
you
they
can complete the
prioritize that.
checkout, right?
Yeah, yeah. If the customer wants to buy something, let's not get in the way of that. That's what they want more than anything else. So that's another kind of fundamental thing you have to think about in designing systems right from the start. Now, the good news is, I think, we can punt a lot of problems onto storage systems. So that's what my interest for a long time has always kind of been centered around storage systems. Because I think if you think about a typical simple website, right, a 2 to 3 tier website, there's lots of problems of concurrency
Hmm.
that could come up in a web server. But what we tend to do is say, yeah, don't do that, right? So in a web server, when a transaction comes in, open a transaction with the database, you talk to the database and nobody else, and then you finish the transaction and you let the database take care of all the concurrency problems and all the consistency problems for you.
Right.
Because it was written by grown-ups and it's been developed over many years, and they're really good, right? They're mature technologies. So just let them take care of those problems, and don't, avoid ever having your your two concurrent transactions on a web server start talking to each other directly and trying to negotiate things, because
Right.
that way lies complexity. And in distributed systems, I think we kind of do the same thing. This seems to be the trend, I think, in a lot of systems now. A lot of the interesting work is being done in distributed storage systems, distributed databases, object stores, and they're getting to the point now that they are becoming really good transaction engines, where you could have, you kind of maybe the storage system itself is a big distributed system, and there's tremendous amount of effort going into building that and making it robust. But then everybody who gets to use it can kind of turn over a lot of the hard problems to the storage system, right? This is how most serverless systems work, right?
Right.
Lambda functions. You say, I'll just do my isolated little bit of work, and I'll talk to the distributed storage system, and it will handle all the coordination problems between all the other nodes. And
Right.
so that's kind of a nice, a nice result that makes it, very doable for a lot of engineers without having to kind of devote your life to understanding all the complexity that could ensue. So I think that's kind of a really promising and really exciting area in distributed systems is, our storage systems are just getting so much more mature than they used to be. And they are getting to be genuinely like large scale and high performance and strong, consistent transactions. And once you kind of got that, it's like, oh yeah, there are other things we do in distributed systems, but it's like a lot of our basic applications can kind of work that way. And
Right.
and if you think about it, a lot of what causes large scale is having lots of customers. And the problem is, yeah, their data interacts, but you can also, it's like each one is, there's a human sitting at a laptop somewhere clicking, right? That's what drove
Yeah.
some action on an application. And you kind of do just want to handle that as independently as possible, but coordinate data with others. That describes a lot of distributed applications, every social network ever out there, pretty much. And a
Right.
lot of those, that becomes kind of a design principle. It's like, well, try to isolate all the pieces and make them as independent as you can, and minimizes the points where they talk to each other. And if you can let a mature existing storage service take care of that for you, great. If you need to build a new storage service to make that work, maybe that's worthwhile too. We've seen a lot of systems out of some of the big companies come from exactly that motivation. It's like, yeah, we want to just have these independent, shared nothing nodes handling transactions and negotiating everything. And then there's a storage system and that's where all the crosstalk happens. And so we're going to go and devote some engineers to building a good storage system and then make life easier for everybody else. So I
Right.
think that's another kind of fun pattern that's come out that makes a lot of practical, really large scale, interesting applications actually surprisingly easy in the modern landscape.
Your point about like partitioning data, I hear the term like single player versus multiplayer apps thrown around sometimes, particularly in like the business to business SaaS world. So you can imagine an app like Google Workspace or I don't know, Jira, right? A lot of these kinds of apps have kind of I've heard it called a tenant model. Well, they'll actually have a separate database for each individual customer because they've decided kind of at the business level, our customers don't care about each other. Like the only reason we're using a client server model at all is so that things kind of nicely persist in the cloud. But things get really simple when you can just be like, oh, it's single player. Whereas if you're working in a domain like a live video game, right, things get a little more hairy, trying to keep everything in sync.
Yeah, and I just want to clarify a difference between, so partitioning your data up and making a bunch of small versions of the problem, that's what you're describing, and that's a good way to tackle, if you can. That's kind of a nice way to be able to do things. The partition problem of the CAP theorem, though, is a networking phenomenon where a backhoe cuts through a cable, and for a little while there, it could be that your network is just broken or a switch is misconfigured. Or a malicious actor decides to direct all network traffic that was supposed to go to, South Korea, and they somehow route it to North Korea, right? In order to, for some state security reason or whatever. And so your network fails, and we can't make perfect networks. The way our network
Right.
works, you'll get these divisions where failure of equipment or failure of configuration leads to machines that are working and talking to each other and talking to different parts of the world, but sometimes they can't. Different groups of the data center on the East Coast can't talk to the data center on the West Coast, but they can each talk to their own customers. And
Got
so
it.
it's not a deliberate partitioning; it's an error condition where for some amount of time, your big system with hundreds or thousands of nodes, they can't all talk to each other. You can't send a message from any arbitrary pair. The whole thing has been partitioned up in some way.
I want to run that
Um,
back to make sure I
now the
understood. Just
sure,
really quick. So, I think sometimes it's easy to think about the internet in 2023 as like the internet. It's the interwebs,
yeah,
and either you're connected to it or you're not, right? But
yeah,
what you're saying is essentially, I think, that you have all these different nodes on a network. Maybe it's the internet, but for whatever
mhm,
reason, like it's not that like one node, or maybe it's not necessarily that one node is just completely isolated, but that you have like a partition of the network. So some nodes are able to talk to other nodes, but those nodes maybe aren't able to talk back, or you get like weird
yeah,
cycles in your network graph. Is that
yeah, yeah. A may be able to talk to B. B can talk to C, but A can't talk to C.
okay? So this like really
Right?
only
That
happens when things
all
like really go wrong at the network level, I would imagine.
Yeah, all those things can happen. I mean, the most common and kind of simplest to think about is, can you have a cluster of 10 machines and four of them can talk to each other in a clique and six of them can talk to each other in a clique, but none of those three can talk to, or none of the four can talk to any of the six.
Mm,
And usually it's a temporary condition, right? Hopefully you're monitoring your network and you fix it. But while that's happening, there's you've got this weird thing where your system, the nodes can't all talk to each other, and you have to have made the decisions in the design back at the beginning of what do we do when this happens.
now you have two
You know,
Kubernetes clusters.
yeah, and we try not to let that happen because it's a mess, and it's hard, but you can't eliminate it. That's
Right.
always going to be a possibility. And then when you start thinking about like mobile devices, yeah, they're partitioned from the network individually all the time, right? There's a
Yeah.
much kind of smaller version of that problem whenever you use a laptop and the Wi-Fi is flaky, or you use your phone and you drive through a tunnel, right? Those applications that were relying on connectivity are now temporarily partitioned. Your cell phone is working fine, the server's working fine, most of the network's working fine, but temporarily you can't talk to it. What happens to the user experience while that's going on? And
Right.
hopefully it doesn't involve data corruption, right? That would be a
Yeah.
failure of your design. Um, but that idea of just partitioning your data up and making many smaller versions of the problem, in a lot of instances, that is a great solution. If you can do that,
Right.
absolutely do that. That was the yeah, that's behind a lot of systems, I guess. To the extent that you can do that, Gmail.
Yeah.
Um, One Gmail user has a lot of interest in their own data and they don't really look at other people's Gmail data, except when they send messages, and that's kind of an external event.
Right.
Same for Google Drive, same for, in any kind of application, you're working on a document. Maybe you're doing a shared document and there's a small number of people collaborating on it, but the rest of the world is completely independent during that time.
Right. My team
Um,
is an isolated unit, essentially.
Yeah. And so yeah, if you can organize your data so that you effectively have little mini servers that are just serving a small group of people, and then the mini servers have minimal communication with each other, then that's a great model if it works for your application. And what
Yeah.
that does is reduce the problem to one that fits on one machine.
Yeah. Yeah. We
Right?
like
Or at
that.
least the part of it you're interested in becomes a server that's independent of all the others. And that, again, even if it's not really one machine, making it so it effectively is for some sub part of the problem is a really effective way to solve problems in practice. In many instances, not all.
Right.
Facebook talked about how, for a long time, every time they'd hire an engineer, they would try to find a way to partition the data up. Say, well, East Coast versus West Coast, America versus Europe, whatever. And the reality of human connections is there was no place you could draw a line and divide Facebook into even two pieces.
Right.
So they really can't work that way. But a lot of applications can, or temporarily, maybe while you were collaborating on a document, dynamically, you can kind of basically agree on one server that everybody talks to, and that's plenty of power for the duration of that session. A Zoom meeting, you limit how many people can talk on one Zoom call, and that limit is partly driven by the resources of one of the server nodes that's coordinating.
Right.
Probably.
That makes sense. You mentioned that there's some interesting technologies out there that are making, like, I don't know if it's necessarily making big advancements in the academic sense in distributed systems, but like at least technologically, we've got a lot of tools these days.
Yeah.
What are some of your favorites? I've worked with Kubernetes and Rabbit, MQ, Google's PubSub. What are some that really pique your interest?
Well, so I don't actually work in the industry. So I can read about these things, but I don't use them. And I'm also not an academic researcher, so I'm not tracking things as closely. I'm still interested and follow things roughly, but again, the places I look, the ones that I think are interesting, I've always kind of been interested in storage systems. And so, some of the kind of high profile systems there, I think, Google's Spanner was a watershed moment. That's 10 years old now, I think.
Yeah. And
there have been a lot of other systems now that have kind of imitated that or built on, the ideas that Spanner pioneered. Because Spanner is a proprietary thing inside Google's network, right?
You only get cloud access to it, right?
Yeah, right. And so they're open source and other proprietary implementations kind of trying to solve similar problems. And so I'm interested in those, but again, I don't watch them that closely. Every once in a while, I kind of go and dip my toes in just to see what's happening. But I don't, I would hesitate to name any because I haven't actually deployed a real system on one of them and seen, all I can see is what other people have said and what their see if their website looks good or whatever, which is not a very good way to evaluate
the best indicator. Yeah. That actually leads me to my next. Sorry, go ahead.
Please. Yeah.
Okay.
No, I'm done.
Cool. I was just going to say that actually kind of leads me to my next question, which is I've found that some of the most interesting people tend to have interesting places where they get news or their media about what's going on in the industry. Are there any places that you hang out online and maybe even more specifically that you'd recommend people hang out online to get news about maybe even just engineering in general?
Yeah. This is one I feel like I've found fewer places.
It's getting worse.
It kind of is. I was a very early user of Reddit. I think one of the first couple hundred users or something like that. And I barely log into Reddit these days. And I think they used to have really, maybe they still do, I guess, but a lot of it used to be that the entire site was fairly tech focused in the very early days. And then they created the concept of subreddits, and the programming subreddit was a really good place for a while, and Go had a good subreddit for a while. But it seems like that cycle, the social media cycle, where things are kind of great with the early adopters, and then a lot more people come in, and then it kind of loses the quality, and the signal to noise ratio gets bad, and after a while it's just memes and jokes. It seems to be playing in fast forward, and it's not that often I come across now a Reddit community that I do check in, and that's one place I think to surface a lot of discussion. Hacker News is probably the main one. I think the quality of discourse on Hacker News is highly variable, shall I say?
Not high, highly variable.
Yeah, there's some real insight there, and then there's a lot of posturing and people just trying to make themselves look smart, and that gets really frustrating. I don't know of really a better place necessarily. I follow some kind of academic circles on Mastodon, where I've gone and found professors with similar interests, and it's interesting. They really talk. I think I see more cat pictures in those communities and more cooking, people showing what they're cooking and things than anywhere other media that I consume. But then they'll also talk about their work or link to interesting work that's going on, and I think I get a lot of interesting stuff there. But yeah, I feel like it's kind of grim. I don't think
depressing answer. Yeah,
it feels like it's a lot more work to surface the really interesting stuff. I think it was a lot. I think one of the kind of best eras for that was when blogs were really widespread,
Yeah.
and everybody had their own blog, and it was a matter of subscribing to good ones and following but there was always more to look for. And now blogging's kind of fallen apart. You know I,
Googled is
I
a
get some of
disaster.
that from
Yeah.
podcasts. Yeah, I get some from podcasts, but even that, the podcasting market is kind of changing. Too many people um, go to it thinking they're going to get rich, and very few do, and so they all just stop after a while. It
Yeah.
seems like, right? Um, and so I don't know. I feel like I've had my heart broken a lot of times when I go get really attached to a podcast or a blog, and then it kind of fizzles out after a while. And there's interesting stuff on YouTube, but again, YouTube really rewards people who publish consistently, and get engagement in the comments and all that kind of stuff, and that doesn't necessarily lend itself to a really good way for tech discovery. So
Right.
I don't know. If you find a good place, let me know. I
No,
feel like
it's
the information's there. It just seems like it's a lot harder work to find it than it felt like it was in the past.
that's definitely been my experience. I've been mostly jaded by the changes with Google. It feels like every
Mhm.
year I have a harder time finding the
Yeah.
information that I want to find. Um, so I like what you said at the very beginning, which isn't like, it's not a place to go, but I think it's just good advice in general, which is like, if you can go find like smaller communities that are just starting up, sometimes those tend to be better, right? Because you
Yeah.
get more interested people, more interesting people that aren't just like spam their thing to the world, or whatever.
Yeah.
Um,
Yeah.
cool.
I think, and I don't know. I guess that's. I'm not sure how to create that or how to perpetuate that, right? How do you lock it down in that cycle when it's really good? Because if it's good, more people are going to come, and then, um, that brings the good and the bad with it, I think.
Yeah.
So I'm I do think, like, I used Twitter for a while, and I think if you ignore all the celebrities and people with millions of followers, you could find really good little communities. And I think Mastodon has some of that as well. Is probably better for that than Twitter is now, but on a
Hmm.
much smaller scale than what Twitter once was.
Right.
And I think if you can go and find the interesting people, it's just hard work. You have to find them, but you can kind of build a group that you're following that can be a really good, kind of gives you that sense of a small community with a shared interest. And I
Right.
think that's ultimately what I really want out of social media. It's not necessarily people that I know, but people who are all interested in the same thing, and small enough that there's that some sense of people knowing each other and behaving themselves. I guess
Yeah.
I was really um, got into my first computer was an Apple II, and a few years back, probably 10 years now, I kind of said, what's going on? I wonder if anybody else remembers the Apple II, and started listening to a couple of podcasts and things like that, and figured out that there's actually a conference that meets every year and has been since the late 80s. So there's still an Apple II conference running, and I've gone a few years now, and it's the strangest little community, because it's maybe 100 people that come, and a couple hundred more that are participate online and things, but it's almost more like a summer camp. We go and take over the dorms at a college for a week, have presentations, go out to dinner and things like that. And it's like, yeah, I'm interested in Apple IIs, but the best part of it is this weird little community of people who are still really into it and making new hardware for it and things like that. And it makes me just wish there were communities like that in more areas. People you'd actually want to go and meet and hang out with for a week in person.
Yeah.
And I don't know how, I don't know where you find those.
Well, interesting people
Or
are
how you spend
interested in
that
interesting
online.
things, right? Like
Yeah.
it makes sense to me that if you have kind of quirky hobbies, that you'll be able to connect with people that are also into that. Um,
Yeah.
that's good advice. It doesn't need to be Apple IIs, but I'm sure I'm
Yeah.
sure that could be a source of finding people. I like that. I don't want to take too much of your time. Thank you so much for coming on. But I
Of
do want to
course.
just ask one more question, which is,
Sure.
do you have an unpopular software engineering opinion? that you're actually aware of is unpopular?
um, Boy, I don't know how. I have always been an object-oriented programming skeptic, and I feel like it's not even that unpopular an opinion now. But I felt
It
like I was
was,
swimming
right?
against
10
the
years ago,
tide for a
yeah.
long time, and so I feel somewhat vindicated now that I look at, Go isn't especially object oriented. Rust isn't especially object oriented. We've kind of taken some of those ideas, but it was so dogmatic in the '90s, and and well past that era. Um, that Yeah, I really felt like kind of a curmudgeon for a long time. But like I guess my general the way to kind of generalize that is, I think the pathology that was there was an obsession with purity.
Hmm.
And I think that is really a problem in a lot of engineering circles when we become so in love with an idea and we lose sight of the pragmatic uses of it. And we start to just try to take that idea to an extreme and force everything into that framework. So whether that's object oriented programming or whatever, I think once we do that, we just surface all kinds of problems. And it's alarming when we get swept up in an idea like that, and that becomes like the orthodoxy that everybody follows.
Right.
And so, I think I'm always skeptical. I think there are great ideas in object-oriented programming, and there are some applications where it works amazingly well. Graphical user interfaces. Go look at the object hierarchy of like GTK, and it's
Hmm.
astonishing. It's like beautiful, and it's like, wow, this is what OOP was made for. And literally, it was right. It was developed
Right.
alongside the GUI, and so that's always been its best application. But um, I think this comes up in programming languages a lot, where the most interesting languages are the ones that really do have some kind of a strong opinion and bring this ideological purity, and they like push it and say, how far can we go with this idea? I also
Hmm.
think we shouldn't really program in those languages. That's where you develop ideas, and then you bring the best parts of them into a multi-paradigm general purpose language. And those are the ones that people should actually be using. I think we should all go and explore kind of wacky single idea languages and just program enough in them to be able to kind of adopt that mindset and force us to think anew about the way that we program and what we thought was the way we program, and realize, oh, that was actually just one way and there's this completely other idea. And I think that's really valuable as an education tool. But I think if you go and you start writing your applications in some of those languages, you know, I'm
You
not
can
sure
name
it's,
them. Do it.
yeah. I mean, I found that's like something like Haskell, for example,
Yeah.
or Prolog, or um, small talk. I don't know. There are lots of those are the ones that are kind of held up as, yeah, this is like the purest form of
Hmm.
some kind of programming idea. I love functional programming. That's why I cite Haskell. Haskell is a beautiful language, and I think everybody should go spend some time programming in Haskell. But I also think we should all recognize when we come to solve real world tasks that it makes some problems harder, unnecessarily so. It was designed as an academic playground, and it excels at that.
Hmm.
And I think we should kind of let that go. And the scheme community has a lot of this problem too, where they're like, oh, we've made this tool that is so great for solving all problems, everybody should use it. And it's like, oh, this is a great way to learn about and think about programs, but it actually comes with some really ugly warts too. And we can do better. We can bring the best ideas over into languages that that where the language is willing to go to where the problem is instead of forcing
Right.
the problem to come to it.
To
I don't know.
quote,
Maybe that's probably not an unpopular opinion, but it's a it's one where I feel like
it certainly
I think we're,
was at one point, I
yeah,
think.
yeah,
And
with OOP specifically. Like I said, I
yeah.
spent a long time feeling like I was in the wilderness, but I think that idea generally of um, I think it's really hard to balance. So many good ideas come from kind of this idea of purity and taking things to an extreme and forcing the whole world to conform to this idea. But it's a good way. An exploration method. It's not a actually. Almost none of those systems have turned into good tools to use day to day.
Yeah.
It's the pragmatic ones, the ones that recognize messiness, that have have been good.
I've got
That become most useful.
I've got to quote TJ from the first episode of this podcast where he said, pushing to production in Haskell means publishing an academic paper.
Yeah.
I think there's some truth to that.
Yeah.
Great. Is there anything else that is there anywhere that you'd like to plug? Do you have any, I don't know if you have like a blog or a social presence that you just like to tell people about?
I really don't. No, I've been thinking about starting a blog for the last 15 years now, but haven't quite pulled the trigger yet.
Yeah.
So
no worries.
And I use things like I say Twitter and Mastodon. I'm mostly a lurker by now, and when I was using Twitter, I set one of those bots to automatically delete my tweets after a couple of months.
Yeah.
I like those things as personal communication and kind of banter and ephemeral communication, and not as, I'm not trying to create a brand or publish. So I really don't have anything to plug right now. But
right.
I appreciate the offer.
No worries. Thanks so much for coming on. It was great having you, Russ.
My pleasure. Good to talk with you.
Bye-bye.